All right. We are going to return now to the topic of decision making, which we haven't really addressed except obliquely in the logic section since search and game playing. So for a while now we've been talking about updating beliefs, keeping track of what's going on in the world, and now we're going to talk about having desired outcomes in a world that has uncertainty in it. So we're going to talk about what makes decisions rational, and then we're going to talk about utility maximization, and in particular how we can refine our beliefs to get more utility. Okay, so the first concept that we're going to talk about is utility. Here's a little picture of a bunch of different outcomes that you might assign different utilities to. So this is a picture of someone who likes ice cream a lot, isn't such a fan of dogs or flowers, but they're all right. So utilities you can see from this picture are represented by scalar values. And more generally, they are functions from outcomes, that is, states of the world, to real numbers that describe an agent's preferences. So first I'm going to talk to you about an agent that has a utility function, and then in a few slides I'm going to talk about deriving a utility function to describe an agent with mere preferences. Preferences being, this is better than that, that's better than this, and so on. So where do utilities come from? If you have something playing a game, you can understand their behavior as trying to win the game, and assigning more utility to a win than to a loss. So in a game it may be simple, +1 for winning, -1 for losing. And as I just mentioned, what'll come in a bit is a theorem that says any rational preferences can be summarized with a utility function. Okay. What we do sometimes when we're designing agents is we hardwire a utility function and then see what behaviors emerge. So we have the agent understand this outcome is worth this, this outcome is worth this, this outcome is worth this. You figure out what to do. Any ideas for why we might do that rather than hardwiring behaviors in different settings? Sometimes we'll do the latter, but why might we sometimes hardwire the utilities and let the behaviors emerge? Yeah. Yeah, so there are potentially an infinite number of behaviors, depending on the setting, and in many normal settings there are at least a vast number of possible behaviors. Think about the strongest chess playing algorithms out there. They are basically rewarded for winning and punished for losing, and they figure out the moves to play. And so that's how we write code for the strongest chess agents, rather than saying, okay, so if this piece is there, and that piece is there, and this piece is there, then do this. Coming up with a program that would look like that and play chess as well would be very difficult. You might not be able to fit it in memory, the program even. Okay, so the point of utility is to maximize its expectation. So the principle of maximum expected utility says a rational agent should choose the action that maximizes its expected utility given its knowledge. So the world has randomness in it, or at least the agent is uncertain about what's going on in the world. And so whenever it's considering a course of action, it doesn't know what outcome is going to arise. And so it certainly doesn't know what utility it will have. And so it takes, the rational thing to do is to take the expectation of the utility. So for all the possible outcomes, you multiply the probability by the utility that you get from that outcome, and you add them all up. And that's your expected utility. So here's a little drawing of an agent that isn't sure whether it likes a rabbit. I think that's what this drawing is supposed to represent. And so it is uncertain about the utility from interacting with the rabbit. OK, so some questions that we will get to. Where do utilities come from? How do we know such utilities even exist? How do we know that averaging makes sense? And what if our behavior or our preferences can't be described by utilities? So we'll turn to those questions in a minute. Now this is kind of forecasting ahead a little bit about the difference between utilities and preferences. So utilities, there's a number that you assign to every different possible outcome. But to have preferences, all you need to do is to say, this is better than that. You don't need to say, it's not necessarily meaningful to quantify how much better it is. You can have preferences without being able to take a stand on whether it's twice as good or 3 times as good. You just know you like that one better than the other. But for utilities, the magnitude of how good the outcome is matters, not just the ordinal ranking. So let's go to an example where the ordinal ranking is the only thing that matters. The magnitudes don't matter at all. In a minimax tree. So in a minimax tree, let's say these are our outcomes. So the min of this is 0, the min of this is 20, the max of these is 20, so the maximizing agent at the top would pick the right outcome. Now we go over here, the min of these is 0, the min of these is 400, the max of these is 400, same action the agent picks. So this is only one example, but you can think for yourself about why it would be true in general that if you scale the values with a monotonic function, it's not going to change the behavior of a minimax agent. It's not going to change which option is preferred. So the optimal decision is invariant under any monotonic transformation for minimax trees. That is a transformation where order is preserved. So if y is greater than x, then f of y is greater than f of x. Let's see. If y is if y is greater than or equal to x, then f of y is greater than or equal to f of x, I think I should have said. But for average case expectimax reasoning, we do need the magnitudes to be meaningful. So let's look at the same example, but now it's an expectimax tree instead of a minimax tree. So let's just say for this setting that all these chance nodes are 50-50. So what's the value of this node? Bit of review. The chances are 50-50? Yep. 20? Yep. And this one is 25, and this one, well, we'll get to that one in a second. So 20 is less than 25, so you go to the right. What about here? This one has a value of 800. This one has a value of 650. 800 is bigger than 650, so you go to the left. So you can see that when you're in an expectimax tree, if you transform the values at the end by a monotonic function, you will not necessarily preserve the optimal policy. You can sometimes change which outcome is preferred. And intuitively, that makes sense. If you have a 50-50 chance between option A and option B, and you want to know how good it is, you need more information than to just say A is preferred to B, or A is preferred to C, some other thing you're considering. You need to know how good A is, or how good B is. Well, both. So in utilities, the magnitudes are meaningful, not just the ordering. OK, so let's look at an example. Let's say we're getting ice cream, and we're deciding whether to get a single scoop or a double scoop. And let's just suppose in this world you're very clumsy, and if you get a single scoop, you'll manage to keep it upright, but the double scoop will be so top-heavy you might risk dropping the whole thing on the floor. So then if you're going to evaluate whether to go left or right, you have to think about, OK, what's the probabilities I end up with nothing? What's the probabilities I end up with double? How much do I value these 3 outcomes relatively? What are the relative magnitudes of the utilities involved, which will, of course, depend on the person. But basically, the object is to maximize expected utility, and the only real challenges will be calculating or approximating that expectation. In theory, it's pretty straightforward. So that's expected utility maximization. And now, and that whole, those last few slides were kind of based on the idea you have a utility function and now you want to know what to do with it. You maximize its expectation. Now let's consider a setting where we don't necessarily have a utility function that we have any access to, or maybe we doubt that there even is one in principle. Now what I'm going to talk about is how you can derive a utility function based on just the orderings embedded in your preferences. So just from statements like, I prefer this to that, I prefer that thing to the other thing, that is going to actually pin down a utility function within a transformation that doesn't end up mattering. Okay, so if you have preferences, what do you have preferences between? We call these things prizes. These are basically outcomes that you place some value, positive or negative, in. But actually, that statement is getting ahead of ourselves. We're not necessarily assigning a number to any of these prizes. We're just saying you're going to prefer some to others. So there are prizes. And then the other thing that you'll have to have preferences between are lotteries. So a lottery is a situation where the prize is uncertain. With some probability, there's one prize. With other probability, there's another prize. And we write a lottery like this. So this means there's a p chance of getting prize A and a 1 minus p chance of getting prize B. There's a little picture of a lottery. So there's how we could write prize, very simple. This is kind of an atomic object in this discussion. And here we have a lottery, which is composed of our prizes plus chance nodes for getting to them. And the notation we'll use will say that if you prefer A to B, we'll write that as A is greater than B. And if you're indifferent, we'll write it with that squiggly line. Now, what we're going to talk about now is a notion of whether your preferences are rational. So we're not talking about whether your decision-making is rational yet. We're just talking about whether your preferences are rational. And at first glance, that might seem like a silly thing to talk about, like how could someone's preferences be irrational? They're just their preferences. But I'll go through some constraints on preferences that I think you'll agree, if you violated them, would represent an irrationality in your preferences. So here's one example of an axiom for your preferences. That is transitivity. If you prefer A to B and you prefer B to C, then you must prefer A to C. If you don't, we're going to say that your preferences are irrational. And in fact, it happens to me sometimes that I notice my preferences are not transitive. Like a week or two ago, it was the evening. I was on Twitter, kind of wasting time, and I remembered that I should really call the doctor. And then I was thinking, well, I could call the doctor whenever. It's nothing really urgent, but I have some work to do that maybe is a little more urgent. And then I thought, well, I've done plenty of work today. I don't need to do more work. I'll just stay on Twitter. So I preferred, at least temporarily, calling the doctor to wasting time online. I preferred work to calling the doctor, and I preferred wasting time online to work. And so, in fact, something irrational was going on in my brain. But if you reflect on your preferences, you should be able to iron out these blips of intransitivity. And it's probably better to describe what was going on in my head as a competition between different agents with rational preferences rather than one single unified agent. There are costs to irrationality. At least with this one, and I think with all the axioms I'm going to tell you about. If you have preferences that are not rational, that don't obey these axioms, you can be induced to give away all of your money. So here's a little thought experiment for how. If you prefer outcome B to outcome C, and I can arrange that for you, then you would pay me maybe like a cent, some very small amount of money you'd pay me to get to B. And then if you prefer A to B, you'd pay me another cent if I could get you to A instead of B. Likewise from C to A, and you could keep paying me a cent if I had the ability to send you around the circle, and every time you'd be like, yeah, I do prefer that to that. Yes, please, thank you for taking me there. And so then you could be, you'd lose all your money and you'd have gotten nowhere. So if you didn't buy just from looking at this that, yeah, of course, you have to have this property to be rational, maybe this convinces you, because it certainly doesn't seem rational if you end up giving away all your money. Okay. If you want like an example for what it means for me to be like giving you different prizes. So say I'm selling produce and I have an apple and a banana and a carrot, and I'm saying, okay, well, I'm about to give you a banana unless you want me to give you an apple instead, and so on. Okay, so here are the other 4 axioms of rationality. The first is orderability. For any 2 outcomes, you're going to prefer one or the other, or you're going to be indifferent. So, I mean, ultimately, you're going to have to make decisions about things. You have to have a preference between any, or you won't care. Transitivity, I just told you about. Continuity is that if you prefer the apple to the banana to the carrot, then there's some probability p where you'd be indifferent between the banana and a lottery between the apple and the carrot, where you get the apple with probability p and the carrot with probability 1 minus p. So it's not going to be the case that like banana versus 90% chance of apple, 10% chance of carrot, definitely taking the apple, definitely taking this lottery. But if it's an 89.999%, then I'm definitely taking the banana. There has to be some probability in there where you are in fact indifferent. It's not going to, as the probability is going from 1 down to 0, you're not going to suddenly prefer you're not going to suddenly prefer B to the lottery. It'll at some point in there you'll be indifferent. So that's the continuity assumption. The substitutability assumption is that if you're indifferent between A and B, then you're indifferent between lotteries where the only difference is that you swap out A for B. So if I'm indifferent between an apple and a banana, then I'm indifferent between the opportunity to have an apple or a carrot with 50% odds, or a banana or a carrot with 50% odds, because we've already decided I'm indifferent between apples and bananas. Doesn't matter the effect of throwing in the possibility that maybe I'm going to get some other thing. Yeah?
So the tilde means indifferent?
Yes, that's right. Yep. And as a reminder, these less thans and greater thans, they're not scalar values that we're saying is one's bigger than the other. This is just notation, and it means you prefer one to the other. And lastly, monotonicity. If you prefer A to B, and you're considering lotteries between A and B, you prefer the lotteries that put more probability mass on A. If you prefer an apple to a banana, then you'll prefer a 60% chance of getting an apple and a 40% chance of getting a banana to a 50-50 chance. Anyone doubt any of these? Anyone think that you can be rational while disobeying one of these? Yeah. Or another question. It's the greater than less than symbols are for saying you prefer one to the other.
So then for monotonicity, are these actual
Oh, okay. This one is like a normal greater than or equal to sign between numbers, because these probabilities are numbers. This one is not, and really this should actually be greater than or indifferent to, like prefer or indifferent to. So this straight line should really be a squiggly line. Yeah. Yeah, so these are lotteries, these are things you can choose, and so this is saying you prefer this to that one. Any other questions? Yeah. Continuity, yeah. Let's say, well, there's going to be a slide that goes into this example, or into an example like this a bit more. But let's say I'm offering you either $100 guaranteed or a lottery where you might get nothing and you might get $200. Okay? If your probability of getting $200 is 0, you're probably going to take the 100 guaranteed, right? If your probability of getting the $200 was 1, you're going to go for the lottery, right? As we scale that probability from 0 to 1, there's going to be some point at which you're indifferent between either taking the $100 guaranteed or taking the lottery between the 0 and the $200. It's not going to be the case that, like, at a 37.615% chance you want this, and at a 37.616% chance you want the other thing without ever having been indifferent in the middle. So there exists a probability such that you're indifferent between these two outcomes. Yeah. Any other questions, or can anyone offer a situation where they think it would be reasonable to have preferences that don't obey this? Okay. Yeah, I'm not going to wait for oh, yeah? Yeah. So really, anything besides the following is a bit sloppy. Really, the best way to think about these are entire life histories. Would you rather have the entire life history that looks like this, or the entire life history that looks like that? History/future, like a whole life. Which life would you rather have, basically? And so, yeah, if we're talking about like actual physical objects, then it's not really, it doesn't really make sense to say, oh yeah, A is always preferred to B, because the whole context affects the answer. So really, we should think about these as preferences over, well, this says preferences over states of the world. And even that can get a little messy if you think that combination, like different sequences of states of the world will depend on the, or like you might prefer going from this state to that state over going from that state to this state. And so really the only thing that has no philosophical problems, in my view, is talking about preferences between whole lifetimes. Yeah? Oh, yeah, sorry. The question was, what do we make of the fact that your preferences might change in different contexts? So you won't, you know, sometimes you'd rather have an apple to a banana, sometimes you'd rather have a banana to an apple. Yeah. Yes?
What does this mean? The right now.
Implies?
It's not an implied one, like this. A greater than B now.
This one? That one? This one?
Yeah.
That means indifference. That means you're indifferent between the two options. So the possibilities are you prefer this one to that one, you prefer that one to this one, or you're indifferent between them. That's the notation. Okay. And in fact, that's what this thing says. It's going to be one of those three things. Okay. If you satisfy all of those axioms, rationality confirmed. And then the theorem that follows from this is that your behavior can be described as the maximization of expected utility for some utility function. So now this is a claim. There exists a utility function that will describe your behavior if you have preferences that satisfy these axioms. And here is the utility function. Well, here's enough to describe the utility function. If you prefer A to B, then the utility of A is greater than or equal to the utility of B. This is for prizes. And then for lotteries, the utility of a lottery is basically the expected utility of the outcomes. So it's the probability of this outcome times the utility of that outcome, plus the probability of the next outcome times the utility of the next outcome, so on for all the outcomes with all their associated probabilities. And this will ensure that if you'd ever prefer this to that, the associated utility for this will be greater than the associated utility for that, taking into account lotteries and expectations correctly. The theorem says there exists a utility function that matches your preferences. In fact, there will exist infinitely many utility functions, but they'll all be related to each other. Yeah, you have to be a little careful there, but basically they will all be related to each other. And in particular, if you add a constant to a utility function, that's never going to change optimal behavior. If you scale your utility function by a positive constant, that's never going to change optimal behavior. And so these are positive affine transformations. You can basically multiply your utility function by a constant, by a positive constant, and add another constant, and get the same recommendations for how to behave. Yeah.
So is our utility functions always linear?
I think it depends a little bit on what you mean by utility functions being linear, but linear transformations preserve optimal behavior. So if we went back to your utility function doesn't have to be linear in the sense that the utility of 2 bananas is twice the utility of 1 banana. It doesn't have to be linear in that sense. But it is linear in the sense that, where'd this go? If this wasn't an x squared, if this was a 10x plus 7, it would be okay. It would preserve optimal decision making. Okay. So the maximum expected utility principle is choose the action that maximizes expected utility. And if you're rational in the sense of maximizing expected utility, that doesn't necessarily mean that you are explicitly thinking about utility, or that you've heard the term utility, or that you have any idea about what probabilities are. You could somehow, a bit miraculously maybe, be coming up with the actions that are maximizing expected utility without ever having thought about that being your purpose. So for example, a lookup table can play perfect tic-tac-toe and maximize expected utility if its utility is about winning, all without ever thinking about utilities or probabilities or anything like that. Okay, let's talk a little bit about human utilities now. And we'll think about this question for a bit. Let's say you're spinning a wheel, and if it lands in that black region, you instantly die. And if it lands in the green region, nothing happens. Or you can pay some amount of money to pass. That, if we find the amount of money where you're indifferent, you don't mind which of the options, then that'll tell us something about your the relative utility assigned to being X dollars richer versus being alive at all versus dead. Okay, so what numbers are these utilities? They map states to real numbers, or they map lifetimes to real numbers, if you prefer. The standard approach to assessing or eliciting human utilities is as follows. So we're interested in what the utility is of some prize A. We can compare it to a standard lottery, and that is subscripted by a probability that's going to be used in the lottery. The lottery, we get some best possible prize with probability P, or we get the worst possible catastrophe with probability 1 minus P. And then, okay, so here's an example of that. Either you have to pay $50, or you enter this lottery where there's some chance of no change and some chance of instant death. And then we adjust the lottery, the probability, P, until you're indifferent. And then the resulting P is the utility of this thing on the left, the prize we're considering. And what you'll notice is this means that the best possible prize has a utility of 1, this worst possible catastrophe has a utility of 0, and everything else will have a utility somewhere in the middle. If that's option 1 and that's option 2, show of hands, let's say P is 1 in a million. Which are you doing? I'll give you a bit of, if you're interested, a millionth of a lifetime is about a half an hour. Do you want option 1, you pay me $50, or option 2, I might kill you? Raise your hand. Well, just put up a 1 or a 2. Okay. Yeah, plenty of both, really. Yeah, okay. So 1 in a million is about, I wonder if I'd said a totally different number if I'd still have gotten a pretty even mixture of answers. But yeah, I think I'd choose to pay $50, but you know, it's in the range of reasonable for both. I mean, we routinely face 1 in a million chances of dying. I think. I can't remember. I don't know about how routinely, but you definitely do. Certainly, if you're talking about like moving somewhere where you'd have to commute, and then you're driving an extra half an hour every day, you know, that changes your probability of dying this year by, I think, more than 1 in a million. Okay. It would be tempting to think that, you know, if you're dealing with questions of money, that your utility is just how much money you have. Maybe not so tempting, but some people have made that mistake. So we can talk about the utility of having money or being in debt. So we can distinguish two things, the utility and the expected monetary value. So let's consider a lottery where you have a probability P of getting X dollars and the remaining probability of getting Y dollars. The expected monetary value is just the expectation of the number of dollars you'll get at the end of the lottery. So that's P times X plus 1 minus P times Y. Before moving on, any questions about that, about the expected monetary value? Okay. The utility that you get of this lottery is P times the utility of having X dollars plus 1 minus P times the utility of having Y dollars. These could be pretty different. Typically, in fact, the utility of a lottery is less than the utility of a guarantee of the expected monetary value. And in this sense, people are risk averse. So here's an example. How much would you pay? I mean, think about this in reality. Like, how much would you pay me coming up right now for a lottery ticket where it's 50-50, you get nothing or $10,000? Would you, I mean, would you, in fact, knowing your financial situation, come up here and say, I will give you $5,000 for this, which is the expected monetary value of this lottery? Or would you not be willing to do that? Would you only be willing if I was offering it for like $1,000 or maybe even less? So just think for yourself. I won't ask you to put up hands for this one. What's the sort of number where you'd think like, yeah, maybe I could go either way on that in terms of having that? And you'll probably notice that it would be less than the expected monetary value. The certainty equivalent of a lottery is the cash amount such that you're indifferent between getting that cash versus playing the lottery. This is a mistake, sorry. This should be the utility. Wait a second. Nope, not a mistake. Sorry. I thought it was improperly typed. Okay, yeah. So this is a lottery, and this is a lottery, and this is a prize of some amount of money. This is an amount of money. This is an amount of money. That means we can subtract them, and that's called the insurance premium. And if people were risk neutral, this would be 0. So what people do when they're buying insurance is they pay an insurance premium to get out of a lottery that they're in, but they don't want to be in. So you don't necessarily want to be in the lottery of being out however much you're out if your house burns down. So you're in a lottery. Every day your house could burn down or not. Every day cyber criminals could take your company's data if you own a company, or not. Or you might die and leave your children without any income. And these lotteries, the bad outcome is so bad that people are willing to pay money to get out of the lottery, and the expected cost to the insurance company is less than the amount of money you'd be willing to pay to get out of that. So you pay them, and they insure you, and they compensate you if these bad things happen. And both parties win, at least in theory. There is an opportunity for both parties to win. Yeah? Oh, yeah, sorry. That was, I just skipped over that. So this is, I think these come from like psychology studies, which are trying to map about, this is the amount of money people have, and this is how their utility from that. And you can see that especially for positive values of money, that people are risk averse because it's concave down. So if you look at a point like here and a point there, the utility of lotteries will be somewhere on a line connecting these, but the utility of just having the expected monetary value of the lottery is going to be greater, typically. You'd rather have the certainty of a slightly smaller amount. So in fact, you get a different effect if someone is way in debt. They don't really care how much in debt they are, and so they'd rather have like some small chance of getting out of debt, and they don't mind a relatively large chance of being even deeper in debt. So this is maybe a bit of a more accurate picture, at least when we get to very negative values of wealth. And in fact, yeah, I'll take a question first.
Can you explain the certainty equivalence again?
Yeah. So let's say there's a lottery where you have a 50-50 chance of getting $10,000 and a 50-50 chance of getting nothing. Let's say I offer you that lottery, or I'm offering you this suitcase with X dollars in it. For some X between 0 and 10,000, you'd be indifferent, right? For some X, you'd want the suitcase. For some X, you'd want the lottery. For some X, you'd be indifferent. And whatever that X is, that is the certainty equivalent prize, where you're indifferent between that and the lottery. So I don't know, maybe it's 1,000, 2,000, 4,950, I don't know. So a certainty equivalent of a lottery is a prize, basically. Or if we're talking about money, it's a dollar amount. If we're talking about the dollar amount of how much you consume in a year, typical, the logarithm of that number is a pretty good match for a utility function for people. So generally, like consuming goods and services worth $100,000 is about halfway between, in terms of utility, consuming goods and services worth $10,000 versus $1 million. So if you had a lottery between getting to consume a total of $10,000 versus a total of $1 million, and it's 50-50, a lot of people would be roughly indifferent between that and $100,000. This is not like in addition to your other consumption. This is like if that's all that you're allowed to consume in a year. Okay. So that's, we haven't talked about time, and just as we went from Bayes nets to hidden Markov models, kind of adding in a time element, we're going to do that pretty quickly here. So now we're going to talk about utilities of sequences of prizes, because we are all beings that exist over time. We don't just exist at one point in time. So what preferences should an agent have over prize sequences? So here are kind of two different possibilities. It's the same prizes, but here they're all coming at the end. Here they're coming along the way. On the question of more or less, you know, this is a pretty uncontroversial option. I mean, you're getting, for the one on the right, you're getting more at every point in time, so clearly you should prefer the one on the right. Now or later, well, that's a more challenging question to try to answer. Would you rather get the prize on the third time step or on the first time step? Maybe you should be indifferent between these. Maybe you'd slightly prefer this one coming sooner. Those are both pretty reasonable options. So if we add one more assumption about preferences, and I'm not going to call this necessary for rationality, but if you're inclined to, you're welcome to. This is one more assumption about preferences that would lead to a constraint on your utility function. That is, if you prefer this sequence to that sequence, then prepending an identical prize to each of those sequences should preserve your preferences. So let me say that again. Here's one sequence of prizes, A1, A2, so on. Here's another, B1, B2, and so on. And if you prefer the sequence of A's to the sequence of B's, then you should also prefer C followed by the sequence of A's to C followed by the sequence of B's. So this is the same C. So that's an assumption you might make about what are some constraints on rational preferences over sequences of prizes. Any questions about that assumption? Okay. If you make that assumption, then the utility function has the following constraint. The utility function of a sequence of outcomes, or of a sequence of rewards, basically, utility is assigned to each of these prizes. It must take the following form. You basically have to care about this first one, some amount, and the next one by gamma times that amount, and the next one gamma squared times that amount, gamma cubed, gamma to the fourth, so on, where gamma is some number between 0 and 1. And that's called the discount factor. So if your preferences obey this property, then the utility function, which you'd want to maximize the expectation of, must obey this property. Only option. If you have infinite sequences, then putting gamma to 1 could run you into some trouble because the sums might not converge. But if you have finite sequences, then 1 is okay. Questions about that? Yeah.
I'm kind of confused on like the significance of the first stationary preferences. Like, it's just saying if you add the same reward at the beginning for each of the sequences of preferences
Yep, that's exactly right. So if you're considering some sequence of outcomes, like, you drive to San Francisco, you go down Lombard Street, and then you get an ice cream, versus you drive to Marin, you go to Muir Woods. If you are you'll prefer one to the other of those. And then if you change the question, now the question is get a haircut, drive to San Francisco, go down Lombard Street, get an ice cream, versus get a haircut, drive to Muir Woods, go hang out in Muir Woods. Whichever you preferred in the first setting, you'll prefer the same thing in the second setting. Adding to the beginning an identical possibility isn't going to change it. Yeah.
It seems to me like if you had a set of discount factors for each time period, like that stationary preference property would still hold. Why do we have to have the same discount factor for each time?
So let's say that for the next 100 time steps, your preferences work one way, and then for the 100 time steps after that, they work a different way. Then this one wouldn't hold, because pushing it back would push one of those prizes from the first phase to the second phase, and that could change your overall ranking. So in the situation you're imagining where you're kind of changing your attitude toward the distant future as time goes on, it's true that your utility function would not take this form, but your preferences also wouldn't be stationary. So this would break, and so we shouldn't be surprised that this breaks as well. Yeah.
So this doesn't mean that order doesn't matter, so order can still matter. It's just that if you have something in the beginning for both steps, it's going to be the same preference, I guess.
Right. So this doesn't mean order doesn't matter. In fact, since this, let's say gamma is really small, like 0.5, then if one option, it's like better at the first time step but worse at the second, and this one it's obviously worse at the first time step, better at the second, then switching the order around will change which you prefer, because you care more basically about the first time step than the second. So yeah, the order could change. Yeah.
Why is the sequence that we're sending over infinite?
It doesn't have to be. It's just written that way in the most general form, I think. Yeah, it could be infinite, it could be finite. You could imagine a setting where all your prizes are 0 after some finite time. So that's why I think this is a slightly more general form. But I don't know. Do you not aspire to live forever? No. Yeah.
Is the discount factor, would a good one be like 0.5 or greater, since it's not like 1 minus? Do you use like 0.9 as a discount factor, for example?
Yes. The discount factor could be smaller than half, though. I mean, it starts to get a little insane. Like, if the discount factor was 10%, then basically you'd sacrifice basically nothing to get yourself anything a year from now. So if the discount factor was 10%, then you care, I think 8/9 of what you care about happens in the first time step. So like this is worth a full amount. This is kind of only 10% as important. This is 1/100th as important. Things start to become very irrelevant very quickly for discount factors. As a rule of thumb, if you do 1 divided by 1 minus the discount factor, that's about how far into the future you care about. So if you have a discount factor of 0.99, you're kind of caring about the next 100 time steps. Like most of what you care about is in the next 100 time steps. If you have a discount factor of 0.999, most of what you care about is in the next 1,000 time steps. Yeah. Well, you could have gamma be 1 and not discount. Does that answer your question?
Yeah, but
Why do we care about what? Oh, it's just to say if you had a discount factor that was smaller than 1, it's hard to say you're being irrational. That's basically what this says. You'd have to make stronger assumptions in order to say that that's the only reasonable utility function. So if you're only making this utility function, if you're only making this assumption, then utility functions with discount factors less than 1 could be reasonable. If you make other assumptions, maybe it would suffice to say that you're indifferent between orders, then I think if you make that assumption, then the only utility function would be just the sum of all these, discount factor of 1. Yeah?
Is it possible that you kind of progress in one of the sequence and then at a specific point, because of like your movement in the sequence and the future reward is coming closer, and you kind of prefer the other sequence in the middle? Is it possible?
Yeah, humans do that, and so we probably don't, this probably doesn't hold for us. And moreover, we see things in the world, and that changes how we prefer things, or we learn about what we want. And so yeah, as I said, I'm not as bought into this assumption as I am to the others. Okay, let's get on to decision networks and the value of information. And this is going to deal with the fact that sometimes the probabilities of different outcomes, depending on what we do, are not perfectly straightforward. We actually have to compute them. Okay. So here is a very simple a very simple decision network, although we'll look at an even simpler one in a minute. This is saying you can decide whether or not to take an umbrella. This is a random variable, basically, as to what the weather might be, which affects the forecast, and which will affect your utility. In a decision network, we choose the action which maximizes the expected utility given the evidence. So that's what we're going to be doing. And we can operationalize this with decision networks. They're basically Bayes nets with nodes for utility and action. And they let us calculate the expected utility for each action. So there are some new types in here you might have noticed. We have chance nodes like before. These are rounded. But now we also have actions, which are rectangles. They can't have parents, and we'll treat them as observed evidence when we're taking expectations. And then we have utility nodes, and these are going to be diamonds, and they will depend on action and chance nodes in general. Okay. So for action selection, what we do is we instantiate all the evidence. If we've seen anything, we set those nodes to the values that we've seen. We set action nodes in every possible way that we're considering. We calculate the posterior for all of the parents of the utility node, given the evidence. And then we calculate the expected utility for each action. This lets us choose the maximizing action. So that's going to be the general procedure here, which you can read over again while you do the attendance code. Any questions about how this is going to work? Okay. Oh. All right. Okay, now let's look at an even simpler decision network to go through an example of how to maximize expected utility. So here we have a weather variable, and let's say, given by this decision network, is the following probability table. So there's a 70% chance of sun, a 30% chance of rain. These are the 4 different possible outcomes, depending on whether you take an umbrella or not. And these are the utilities associated with those 4 outcomes. If you leave an umbrella and it's sunny, you get 100 utility. If you leave the umbrella and it's rainy, you get 0 utility. If you take the umbrella and it's sunny, you get 20 utility. It seems a bit low to me, but all right. If you take the umbrella and it's rainy, you get 70 utility. So let's set umbrella equal to leave. And now we can say, what is the expected utility of leaving the umbrella? Well, we sum over all possible weathers of the probability of that weather times the utility of that being the weather when we have left the umbrella. So in this example, that's 0.7 times 100 plus 0.3 times 0, which equals 70. Any questions about how we calculated that expectation? Okay. Umbrella equals take. Let's consider the expected utility when we set this variable to that value. Same expression as before, but now we're looking at the utility of weather when we take the umbrella. 0.7 times 20 plus 0.3 times 70 is 35. So the optimal decision here is to leave the umbrella because the expected utility is higher. So this is the maximum expected utility, and I'll explain for a minute why this empty set symbol is there. But the maximum expected utility is the maximum over actions of the expected utility of that action. So just take notice of the notation here. Expected utility is a function which takes an action as an argument, and then it returns the expected utility. And the behavior of this function is determined by the decision network and the various tables that compose it. Okay, so as I was getting ahead of myself a bit. Expected utility of leave is the expected utility of taking action leave, and so in the parentheses we write an action, and calculating the expected utility requires taking an expectation over the chance nodes, over the outcomes of the different chance nodes. And then the maximum expected utility is written like this, given no information. We'll talk about this setting where we have some information later. So in the parentheses, we write the evidence, that is, which nodes we know the value of. And calculating this requires taking a maximum over several expectations. Basically, we do an expectation for every action. So let's kind of rewrite this problem as a decision tree. Here's our action node. We can either take the umbrella or leave the umbrella. These are chance nodes. What's the weather going to be? Either sunny or rainy. And then there's utilities for the different 4 options. So it's almost exactly like expectimax. There's one change between this form and the decision tree form. Can anyone tell me what it is? So in our problem, these have to be the same. The weather doesn't get to look at what your action was, and then the probabilities might change. In this setting, it doesn't change. And that means that this is going to be a more compact way of writing it as the problem gets much bigger. So yeah, it's not really like these are happening in sequence. They're kind of happening at the same time. And so that amounts to these having to be the same in our setting. Okay. Now let's go back to the slightly bigger but still small decision network where we don't observe, well, we didn't observe the weather before, but now we get to observe something, which is a weather forecast. And let's say that once we've observed that the forecast is bad, these are our new posterior probabilities over the weather. So this is the probability of the weather given that the forecast is bad. Now it's only a 34% chance of sunny and a 66% chance of rainy. So let's consider the different expected utilities for our different actions. And now we write it like this. The expected utility of leaving the umbrella, given the forecast being bad, is equal to the sum over different possible weathers of the posterior probability of the weather, given that the forecast is bad, times the utility of leaving the umbrella when that's the weather. And so that's going to be 0.34 times 100 plus 0.66 times 0, which is 34. Same computation, but now for taking the umbrella, different numbers, different answer. 53 is the expected utility. So now the optimal decision is to take the umbrella. Unsurprisingly, hearing that the forecast is bad could change your decision about whether to take an umbrella. And we write the maximum expected utility like this. Before we had an empty set here because there was no information we were conditioning on. Now we're conditioning on this information that the forecast variable takes the value bad. And so this is computed as the maximum over actions of the expected utility of that action given the forecast being bad. So this is as much a slide telling you about how to write this down as about how to compute this. There are various pieces of notation that we use here. There it is again, expected utility of an action given some evidence. The left side of the conditioning bar is the action being taken. The right side of the conditioning bar is the random variables that we know the value of, the evidence, basically. And then the maximum expected utility, this takes an argument, which is the evidence that we have. OK. We can write this as a decision tree again. Before, we just had empty curly braces. Now we have an action that is basically depending on the forecast being bad. And here we have the weather being bad, the weather being bad. Again, these are the same. These will be the same chances of sun versus rain on both sides of the table. And now we are going to talk. Now I'll show you an example of a decision network in Ghostbusters. I think we've seen the Ghostbusters example before. Our action is whether or not, or is where we bust the ghost, if we bust at all. And our utility will depend on the action we've taken and the ghost's actual location. And we'll have these various sensors that we actually observe. We'll observe some of them about the ghost location. So the game here is to make measurements in any of these locations. The measurements give noisy estimates of the distance to a ghost. And we can, if we like, blast a certain square. When we blast, the game is over. And if we have successfully blasted the ghost, we get a utility of 250. So here, there is, the player of this game took a measurement there. The measurement said the ghost is not really nearby, so a little bit nearby. So the probability density of the ghost is higher in this sort of region. Sorry. Oh, the volume sometimes works. OK, so now there are a couple more guesses saying that the ghost is pretty close to there. And now there is a measurement taken there, which means the ghost is very probably there. And either the player has busted or is about to. OK, I think maybe they did. Yeah, and so then once you're 98% sure that the ghost is there, you can say, OK, I'm going to bust at that square. And with a 98% chance, you'll get a utility of 250. Now, these measurements were, nothing I've told you yet would tell you where you should try to measure. These, a person just said, OK, well, these seem like reasonable places to make a noisy measurement. But what I'm going to talk about now is going to give a much more rigorous methodology for deciding how to make good measurements, good helpful measurements. So what we're going to talk about now is the value of information. So the idea is to compute the value according to your utility function of acquiring pieces of evidence. And this can be done directly from the decision network. So for example, buying oil drilling rights, the drill location combined with the oil location will determine how much oil you get. If you drill at the wrong location, you're not going to get anything. If you drill at the right location, you'll get lots of oil. So let's say we have two blocks, A and B, and exactly one has oil in it, and that's worth K. You can drill in only one location. That's all the money you have to do. And your you assign equal probability to the oil being in either of the two blocks, mutually exclusive. So this is the distribution over whether the oil is in A or B. Here is your utility from drilling in A and the oil being there, okay? If you drill in A and the oil is not there, it's 0. Likewise, the other way around. So drilling in either A or B has an expected utility of K over 2, because 50% chance you get nothing, 50% chance you get K. So the maximum expected utility is K over 2, doesn't matter which you choose. So now the question is, what is the value of information of O? What's the value of knowing whether the oil is in A or in B? The value is the expected gain in maximum expected utility from the new information. So if you take a survey, the survey might say that there's oil in A, or it might say that there's oil in B. Either way, whichever you learn, now the maximum expected utility is K, because you can just drill in the place where you know there's oil, you're going to get K guaranteed. So the maximum expected utility is K, whichever this turns out to be. And so the gain in maximum expected utility from knowing oil location is K minus K over 2, which equals K over 2. So your maximum expected utility has gone up when you got this information. So that's called the value of perfect information for the oil location. And that means the fair price of getting this information would be K over 2. So here's a value of information example with the weather. The maximum expected utility with no evidence, as we calculated before, was 70. The maximum expected utility if the forecast is bad, as we calculated before, is 53. Now we can calculate the same thing if the forecast is good. That's 95. And let's say this is the distribution, the probability distribution over what the forecast is. 59% chance it's good, 41% chance it's bad. What is going to be the maximum expected utility of observing the forecast? So with a 59% chance, we will end up with a maximum expected utility of 95. With a 41% chance, we'll end up with a maximum expected utility of 53. We don't know which is going to be. That's kind of the point. We haven't observed the forecast yet. So in expectation, the maximum expected utility will be 77.8. That is the expectation of the maximum of the expectation of the utility. Whereas the maximum expected utility with no evidence was 70. So 77.8 minus 70 is 7.8. And so we say the value of perfect information from observing the forecast is 7.8. And here it is in general. If we've already observed some evidence variables, E, and we're interested in observing the evidence variables E prime, so we know the values that E takes. We don't yet know the value that E prime would take. The way we calculate that is, ultimately we're going to subtract off the maximum expected utility we'd get not knowing anything. First, we take the value summing over all the different possible E primes that we might get, times the probability that we get that E prime, times the maximum expected utility when we have observed the evidence E that we already had and the new evidence E prime. So this is the formula for calculating the value of perfect information. Yeah? For it to be negative. Good question. No. And you'll notice here that if the forecast was bad, the action which maximized this was taking the umbrella, whereas here the action which maximized it was leaving the umbrella. And basically the reason there is value to this information is because it might change your decision. Okay. Here it is again, the value of perfect information. That we consider the maximum expected utility from the evidence we already have. Now assume that we see some new evidence taking some value. The value, if we act then, is written down like this. But E prime is a random variable. We don't know what value it's going to take. We don't know what little E prime will be. So we have to take the expected value if E prime is revealed, and then we act. So the maximum expected utility of little e big E prime is the expectation over little e prime of the maximum expected utility of little e and little e prime. So we don't know what we're going to see. We know we're going to see something. We can think about what the different maximum expected utilities would be depending on what we see. And then the expected maximum expected utility that we'd face when we're considering observing this evidence is this expectation here. So the value of information is how much the maximum expected utility goes up by revealing E prime, big E prime first, and then acting compared to acting now. So the value of perfect information of big E prime, that is observing which little e prime it ends up being, given the evidence we already have, E, is equal to this difference. And here's how you calculate it. So I'll add another picture. We've already seen this picture before, this tree before. And this is, conditioned on E taking some value. Here's another tree conditioned on E prime taking some value. And the setting we're in now is there's a chance node at the beginning for what E prime ends up being, and then two different subtrees, basically this one and its brother, depending on whether E prime ends up being one way or another. So there's a chance node at the top, not an action node at the top, which is what we're used to seeing. There's a chance node at the top. That's going to resolve what evidence we end up observing, and then that's going to change our decision tree at that point because the probabilities down the line will be conditioned on that new evidence. So the notation, which we've been through already, here's the maximum expected utility given some evidence. Described that already. We write the evidence in the parentheses. And this involves taking a maximum over several expectations, one expected utility for each action under consideration. And this is how we write the value of perfect information for knowing the value of E prime, given that we know the value of E so far. So to the left is the random variable that we want to know the value of revealing. To the right is the random variable that we already know the value of. And calculating this requires taking an expectation over several maximum expected utilities. One maximum expected utility for each possible outcome of E prime, because we don't know the value of big E prime. And then each maximum expected utility is going to involve calculating several expected utilities, one for each action, and then taking the maximum. So here's all the here are the equations, which I've described already. So the computation workflow: first, you calculate the maximum expected utility given the evidence you have. Then you also calculate the maximum expected utilities when you add the possible E primes. You do this, you run this calculation for every E prime that could arise. And then you get the maximum expected utility of E followed by E big E prime by taking an expectation over the values of little e prime. And then you can calculate the value of perfect information by taking this difference. Okay, so now let's go back to this Ghostbusters example. Come on. So now the computer decided where to get evidence, and the computer decided that this is the best square, that getting evidence at this square gives the most value of information, has the highest value of information. And note that it costs one to make a measurement, so you have to think about what's the best, which piece of evidence are you most interested in seeing. Sorry, the sound's not working, but I can talk through what he's saying. And now this was the next place they decided to get evidence, and got extremely lucky, actually. And so then after that point, I think the optimal move was just to bust. Getting other evidence didn't end up having value compared to the cost of making the measurement, sufficient value. Okay, so that was a hit. And now there's another example where, okay, now, new example, you've measured here. That was still the best place to do the first guess. The next best place to do the next guess is up there. The best place to do the next guess is over there. These are the cells where the value of information for observing the value of the variable is highest. And now that was the next guess, and now that was the next variable whose value was queried. And now I think at this point it decides that it's not worth making any other guesses. The value of information from observing other variables is too low compared to the cost of making the measurement. And so then it hits it and it gets it right. It's not guaranteed to succeed every time. Sometimes it will, the cost of making measurements isn't worth it and it gets unlucky. But this is how to seek evidence in a careful and, in this case, optimal way. So some properties of the value of perfect information, which someone just asked about. The first property is that it is non-negative. You will never have a setting where you get less expected utility by knowing more, which makes sense. And in fact, it's positive if different observed values of the evidence would lead to different optimal decisions. The next property is that it's sub-additive, and that means this. If there are two variables that you're thinking about observing the values of, the value of observing both of them is less than or equal to the value of observing the first plus the value of observing the second. Consider to see why this isn't equal, you can consider the setting where these are actually the same. Observing the same thing twice is going to be no better than observing it once, certainly not twice as good. So you can see that sometimes, and in fact usually, this is going to be smaller than that sum. And the last is that it is order independent. So observing EJ given the evidence and then observing EK given the evidence plus EJ is going to be the same as the other way around, which is going to be the same as observing them both jointly. This should look a lot like the conditional probabilities and joint probabilities. So the general idea here is that the value of information is the expected improvement in decision quality from observing the value of a variable. So for example, an oil company deciding on seismic exploration and test drilling, a doctor deciding whether to order a blood test, a person deciding whether to look before crossing the road. These are all settings where you can understand how observing the information first will increase the expected utility of whatever action you decide to make because your action can be better informed. And the decision network contains everything needed to compute this property, this quantity. There it is in a different form from what I've showed you. And I'll end with a few quick questions for you to think about. The soup of the day is either clam chowder or split pea, but you wouldn't order either one. What is the value of knowing which it is? 0. It's not going to change how good an outcome you get. There's 2 kinds of plastic forks at a picnic. One kind is slightly sturdier. What is the value of knowing which? Well, there's the cost to you of having your fork break. If you don't know which is which, then that's going to happen with 50% chance. If you do know which is which, then it's going to happen with 0% chance, because you'll choose the other one. And so the value of the information is half of the negative of the cost of having your fork break, because you're avoiding that cost. Third example, you're playing the lottery. The prize will be either $0 or $100. You can play any number between 1 and 100, and if you get the number right, you win, so your chance of winning is 1%. What is the value of knowing the winning number? Well, if you don't know the winning number, your expected earnings will be $1. If you do know the winning number, your expected earnings will be $100, because you'll just choose the right number. So the value of knowing the winning number would be $99, the difference between those. I'm going to skip this slide, and so here are some more questions for thinking about, to think through some intuition here. This is a slightly more elaborate decision network. There's the drill location, there's the oil location, and then there's the scouting report, which changes based on what the oil location is, and then we have the weather that's totally disconnected. So the value of perfect information of the scouting report is going to be, moderate. It's going to be helpful. the value of perfect information of the oil location is going to be better. I mean, better to just know exactly what the oil location is than to have some noisy measurement of it. The value of perfect information of the weather, knowing the weather isn't going to help at all. This is going to be 0. It's not going to change the outcome. Well, we're basically out of time, so I'll skip that one. But here's a kind of general way to think about it. The value of the information value of observing Z given your current evidence is going to be 0 if the current evidence, if given the current evidence, the parents of the utility are independent of Z. So basically, if Z, given what you know, if Z doesn't really have any relation to the parents of the utility,